This is Suvarchala working as an associate professor in Department of Computer Science and Engineering, Ministry of Aeronautical Engineering. As a part of the lecture series on design and analysis of algorithms, in this video, I'll discuss about asymptotic notations. Previous videos, we introduced what is an algorithm, how to represent an algorithm, and what is the importance of analysis of algorithm, and how this analysis is going to be represented. How this time complexity and space complexity are the main parameters or objective parameters to analyze our algorithms, how these complexities are going to be represented, what are the various notations are available. So as a part of that, in this video, we'll discuss about asymptotic notations to represent our analysis parameters of algorithm. That is big O notation, omega notation, and theta notation. These notations we'll discuss in the video so that we can represent any algorithm analysis, its time complexity as well as the space complexity by using these notations. So why this scalability will be considered? In the previous video, we specified the scalability of algorithm based upon input size will be considered as an important issue. So what is more important actually? For example, n is equal to 5, the plain recursion version is faster. If n is equal to more, that is for example 3500 or 4000, 4000, etc., then the complex version is going to be very, very faster. That means depending upon the size of the n, the time taken or the fastness of the algorithm is going to be analyzed. In general, for normal small problems, we need not use our computer science or programming techniques actually. Computer science is about solving the problems people couldn't solve before or solving the problems very fastly comparing with our human processing actually. So that means the emphasis is almost always on solving the big versions of the problem is going to be considered while using computers. So that's why in computer systems, we always will talk about the scalability. That is the scalability means the ability of the solution to work when the things get really big actually. So that's why in any area of computer science, we will consider scalability factor as one of the important factor actually. So as a part of that, for analysis of algorithms also, we will consider the scalability. That is, if n is going on increasing, what happens to our analysis actually. For this particular purpose, we will use growth functions because we can sometimes we can determine the exact time complexity or the exact time taken by that particular algorithm to give a solution can be identified by us. But sometimes what happens, the extra precision usually related to our computing is not at all going to be considered by us. Specifically for large inputs, the multiplicative constants and the lower order terms of an exact running time are generally dominates by the effects of the input size itself actually. So that's why we have to consider the growth, how the functions are growing based upon that, how the input is growing, how the function of time function or a complexity function is going to be increased or decreased along with our size of the input actually. That is, asymptotic notations are going to be used to describe this type of running time of the algorithm, generally in terms of the functions whose domains are going to be any integer numbers or natural numbers actually. What is this asymptotic analysis? This asymptotic analysis is analyzing what happens to runtime or any other event, memory space also, whatever the metric you are going to consider, as the input size n goes to infinity. As limits we are considering in mathematics similar to that, when the input size is going on increasing, then what happens to our analysis of the running time analysis or any other factor of the performance metric of the algorithm actually. The word comes from asymptote, which is we will look at a limiting behavior of a functions as something goes to infinity. In the limits, generally, we will tending to the infinity, we will consider actually. This gives a solid mathematical way to capture the intention of emphasizing the scalable performance. So as going on increasing n, what is the mathematically we will prove that how the input size is going on increasing, what happens to the function of the any metric actually, performance metric actually. It also makes the analysis very, very simpler by using these notations. We can represent as a growth function of that input size. Generally, while comparing, running times are going to be compared based upon, let us assume that growth rates are compared as follows. Let us assume that n is taken values like this. N is 100 n square. N takes the values like this. N is equal to 10 square, 10 cube, 10 power 4, 10 power 5, 10 power 6, etc. That is, we are increasing n value as exponentially. For that, in that particular purpose, our growth functions are going to be, for example, we'll discuss further what is big O of n, 1, n, etc. Let us assume that if n is 100, then the respective growth functions are going to be, it may take 1 microsecond, then 1 microsecond, 1 microsecond, 1 microsecond, 1 microsecond. Because whichever may be the function, it may be order of constant or it may be order of logarithmic, order of n or n log n square, etc. But n going on increasing, please observe that in this table, when going on increasing, these parameters, that is, whatever the functions we are taking, they represent differences in the times actually. For example, one is at 10 power 8. Order of one constant time is same, but when coming to the log into the base 2, 4 microseconds are there. When coming to the order of n, 1 second. Not even microsecond, you please observe 1 second. If it is n log n, 4 seconds. If it is n square, it may be considered to be as 11.7 days actually. You observe this n square is highly increasing as n is increasing. The time taken order of 4, n square is keeping on increasing actually. Now we will compare. Because we compared here constant time, logarithmic time, linear time, and logarithmic time multiplied by the linear time, quadratic time, and so on and so forth you can do actually. That means if this n cube, etc., exponentiation form, you are getting n cube, then as n is increasing, the time taken by the respective functions are drastically increasing actually. You observe the increase of these respective functions, 1 second to the 11.7 days, order of n square, n log n, 1 microsecond to 4 seconds, linear time, 1 microsecond to 1 second, and logarithmic time, 1 microsecond to 4 microseconds. That means this growth rate is very, very high in exponentiation functions. That is quadratic or as well as you can be cubic, etc. We will consider 2 power n and we will compare this quadratic as well as r power square or 2 power n. This is exponentiation 2 power n function. And you observe here, when I am increasing n, a little bit increase is there, not drastically like what we have done previous table. 100, 110, 120, 10, 10 only we are increasing. Even then, your n square increases 1 microsecond to 2.6 microseconds. And if it is 2 power n, 1 microsecond to 37,000 years. Please observe. So that's why any algorithm can be compared based upon these type of order of our growth functions actually. Now, our ultimate objective is if you can represent the time complexity or space complexity or any parametric measure value of an algorithm with reference to these type of functions, growth rate functions, then growth functions, then automatically we can easily compare the respective algorithms actually. So that's why we will try to represent our time complexity or space complexity of an algorithm basically by using any of these growth functions so that we can compare for the same problem, different algorithms can be compared because we understood now which type of growth function is more efficient. As n increases and the time taken by the algorithm is going to be increases drastically if it is 2 power n method function, and it increases drastically if it is n power square, n square, n cube further also. But logarithmic functions are going to be very less variation is there actually. So that's why we will try to compare the respective algorithms, what is its running time complexity based upon these growth functions, so that the comparison will be very easy for us actually. And also comparison, also a uniformity will be there, mathematical based uniformity will be there actually. So for example, if you are considering the time complexity, now we observed, if n is going on increasing, our maximum of n, if you are going to take, the complexities are going to be increasing based upon the respective specifications actually. So practical examples, if you are going to consider, a small examples will take, need not be a program, a small algorithm we are considering. For example, carrying n items from one room to the other room. How many operations are required? Carrying n items from one room to other. What we supposed to do, n items means each item has to pick up first, then it has to move to the room, then we have to drop that particular item there actually. And also we have to come back, reverse move. So totally to move one item, 4 operations are there. One is pick up, forward move, drop, and again come back to the room to pick up the next item actually. So 4 actually. How many such type of items are there for us? N items are there. So totally how many operations are required? 4 n operations are required actually. So 4 n operation means, for example, it may be having some more operations also. Let us assume that the number of operations for each item is constant C. So that's why we consider this 4 n operations can be written as a Cn, that is constant times of n items actually. So that's why if a growth function you are going to represent it as a order of Cn, we will represent that is constant is keeping on changing. So that's why it may be considered as a generalized one order of n. It is a linear function. That means any program that reads an input, this is an example how to find out the particular growth function in normal applications also. For example, another example we can consider locating a patient record in a doctor's office. Various number of records will be there. For example, n records are there. So we have to search for a particular patient record. We can use various kinds of searching techniques are there, which we'll discuss further. And even in data structures, we might have already studied. So binary search algorithm will be there. Sequential search algorithm will be there. Binary search algorithm will take time complexity of log n function. That is because it takes every time half of the list, no? So a tree structure like that, height of the tree will be considered based upon that. Similarly, sequential search means it may start from first element to the last element. The searching has to be continued till the element occurs. So that's why its complexity may be of linear time, order of n. So what is this word we used already? That is asymptotic notations. To represent these growth functions, we need some notations actually. So to represent these asymptotic functions, asymptotic growth functions, we will use this asymptotic notation. Commonly used asymptotic notations are, we will call them as a big O notation, big omega notation, and big theta notation. Of course, along with that, small omega function notations are also there actually. First, we'll discuss these commonly used, more popular asymptotic notation, big O notation, omega and theta notations. Big O notation is defined like this actually. So what is big O notation? When we are using these notations, we will try to represent two functions we will consider, f of n and g of n. That is, the function f of n is asymptotically greater than or equal to the function any g of n or t of n. Then the long run, your f of n is going to be multiplied by suitable constant, which is having an upper bound of t of n. That means t of n belongs to our order of big O of f of n if and only if there exists a constant c and n naught such that T of n is less than or equal to C of f of n for all n greater than or equal to n naught. That means if input size is going on increasing, our f of n is going to be asymptotically increases. Our T of n will show an increase and decrease. Then there is some area, upper bound is going to be decided above which the complexity is not going to be considered. Big O notation, generally we say that an algorithm A runs with big O of n or big O of log n, etc. Algorithm may be big O of n square, etc. Then that the number of operations as the function of input size n, our n log n or order of n square, these cases are respectively actually. Generally, we will use this big O notation. We are interested in asymptotic behavior. Asymptotic means, as we discussed, continuous growth is there actually. As n grows arbitrarily large, but we aware of that large constants can be very significant in actual implementation of algorithms. In such cases, this big O is going to be represented. So that's why big O is represented, our notation is going to be represented asymptotic. We will call big O as asymptotic upper bound. Asymptotic upper bound means we will fix that particular, more than that we time complexity or any analysis of that algorithm, more than that value may not be possible actually. The function f of n is equal to big O of g of n. If and only if there exists, that means those two functions are equivalent. If and only if there exists constant c and n naught such that our f of n is less than or equal to c star g of n for all values of n as well as n greater than 0 can be considered. That means the value of g of n is upper bound of value of f of n. Upper bound means more than that time complexity doesn't exist at all. That is the maximum upper bound. Big O notation can be used to denote all upper bounds. More than that also you can consider all upper bounds on time complexity of algorithm. Big O also captures the worst case analysis of the algorithm. For example, if you are considering this, let us assume that this is our function n and this is function g of n. This represents our upper bound actually. So above that it may be more upper bounds are going to be there, but we cannot use them further. Lower than that it may not occur. There will be some point where both are equal actually. So for certain n value, n naught value, both this cgn and fn are going to be same. Then we can consider this type of big O of notation n actually. So this big O of n can be represented by using this yellow color we consider here. So big O of n means this is the upper bound. Cgn is upper bound. Lower than that only all time complexities will be there. Above that it is not going to be considered. So there may be many multiple things lower that, then we can consider here the respective specifications actually. So when we are using this type of upper bounds here, the specific process is going to be considered to represent our algorithm having the time complexity represented in terms of the big O notations actually. So when we are considering these big O notations, some examples we will consider. Let us assume that two functions we are considering f of n and g of n, where f of n is equal to 3n plus 2 and g of n is equal to n. So we want to represent our upper bound means here, we want to represent our f of n as a big O of g of n. When these two are going to be equal, f of n is equal to big O of gn such that there exists a constant value c g of n is going to be considered. That means in this current example, f of n is less than or equal to c g of n for all values of c greater than 0. We need to find out from which value of n this is going to be considered. That is for all values of c greater than 0 and also n naught greater than or equal to 1. Now we'll solve this problem for c. What c it is going to be considered? What is our f of n? Our f of n is 3n plus 2. So what is our g of n? G of n is n. So that's why By substituting that, our expression becomes 3n plus 2 is less than or equal to Cn. So this above condition is going to be satisfied for what value of C? If C is considered to be as a greater than 3, because already 3n is there now. So 4n onwards it satisfies actually. So the above condition is going to be true for all values of C is equal to 4 and n is greater than or equal to 2. Remember, n is greater than or equal to 2. If it is less than, this expression is going to be lesser value actually. So n must be equivalent to greater than or equal to 2 because it is must be greater than or equal to the constant value you are going to specify. Your C is going to be greater than the coefficient of the n you can consider here. So as a part of that, if you are considering here, my function becomes as 3n plus 2 is greater than or equal to some 4n. So that's why 4n means it is a linear form. It will become order of n. The maximum term will be considered. So that's why 3n plus 2 is less than or equal to 4n for all n greater than 2. Therefore, this 4n plus 2 4n will be considered as a linear order, linear equation, that is order of 1. So that's why big O of n will be represented. Similarly, we can consider other examples also. For example, if you are considering same example, not only order of n, and this is the upper bound, and more below that you can consider, that is order of n square, order of n cube. All of them are also considered to be as a possible complexities actually. But we consider big upper bound means above that may not be possible actually. It captures all upper bounds. For the above example, order of n is the tight upper bound. So that's why rest of all upper bounds are loose upper bounds actually. So if you want to get the correct upper bound, only tight upper bound without having any loose upper bound, small O notation also is a little O notation or a small O notation, we'll call it as it can be considered by us actually. That we'll discuss the end of this session actually. So like that, similarly we can solve multiple problems. For example, 100n of 6. 100n of 6 means 101n will be there. And our C value will be more than greater than 100 now. So that's why minimum value is 101 and the least upper bound it can be considered. And our n value is going to be greater than or equal to 6. Third example, if you are considering 10n square, what is the highest term? Only n square time I have to consider. So it must be 11n square. It must be equal to 11n square more when that is our C value is going to be greater than 10, that is 11. You observe all these examples. What we are considering in these examples, whichever is the highest term is there, that term coefficient we are considering actually. The remaining terms we are not going to consider as much important. The highest term only. For example, if you are considering this example 3, we have 10n n square plus 4n plus 2. We are basically considering this maximum term because the growth rate of n square is very faster comparing with our linear term actually. That's why whenever an expression is there, f of n and g of n we are considering, in f of n we will consider always the priority as the highest degree term will be considered by us. Check the fourth one also, n cube plus n plus 5. We are n cube coefficient is 1. So that's why n cube coefficient we are making it as a 2n cube. Based upon that, the respective n values will be considered. That means here we are try to represent our whatever the expression we are considering this. What is these values actually? When we are getting this means 10n plus 6, 10n square plus 4n plus 2, n cube plus n plus 5. What are all these things? In the last video session, we discussed how to calculate time complexity by using tabular column. So by using tabular column, we got some expression in terms of n. We got an expression in terms of n actually. Based upon that particular expression, we will try to represent it as a growth function actually in terms of any asymptotic notation. As going on increasing, that was considered in terms of n, but as going on increasing, what happens to our complexity, then we considered based upon that particular expressions, based expressions, time complexity expressions only, we try to represent it in the asymptotic notation. For example, let us assume that this is the program we are considering. Small example. What is our example? Print the first element of array. To print the first element of array, how many number of executable statements are there? Only one. Array size may be 1. 1 only. Array size is 10. Then also 1. Array size is 100. Then also 1. Why? Because first element. Irrespective of array size, we are printing only array of 0, the first element. So that's why the executable number of executable statements are 1 irrespective of the size of the n. That is the constant time. So the constant time is represented by using our big O notation as a order of n. So that's why input size may be varying from 1 or 100 or 1000, whatever it may be. But this constant doesn't change here. Because first element means only one statement is going to be executed every time actually. Take another example. In this example, we have print all elements of arrays. All elements of array means, for example, array size is 10. I have to print array of 1, 0, 1, array of 2, etc. So we have to print all elements of array. That is, for example, my array size is 10. Then I have to print a of 0, a of 1, 2, 3, etc. up to a of 9. 10 elements. What is this time complexity here? If array is 10, 10 times we have to execute my print statement. If array size is 100, then 100 times the print has to be executed. That means if array number of elements in array are going on increasing, as per the number of elements, the respective print statements are also, print statement means executable statements are also increasing. That is order of n. Linear time. Where n is the number of items in the array. If the array is going on increasing, the same lines, our number of executable statements are also increasing. That is, in the same lines it is increasing. So order of n times linear time actually. Take another example. Print all possible ordered pairs of array. Ordered pairs of array means array within array we have to use nested arrays. We have to use nested arrays. So how many number of times these are going to be executed? Our print statement, it is within the nested loop. So it will increase first n times within each one loop, again n times. So totally n square times it executes. So our print statements executes n square times. The time complexity of the respective algorithm is order of n square, that is quadratic time actually. Clear? So that's why we are going to consider this type of statements actually. Now, when this big O notation is going to be considered, for example, if you are taking r is equal to x square plus 3x plus 5, instead of you having n, we are considering this x value. Like this only we are getting, no? An expression we are getting. So, an equation we are getting in terms of the quadratic or a cubic or depending upon the nesting of the for loops we are using or any loop structures we are using. So, for example, if this is the expression for different values of x, what happens? If x is equal to 0, 10, 100, 1000, 10,000 and 10 lakhs, etc. we are keeping on increasing. Then what happens? You observe these x square values. X square values are these. Second term x is 3x. Constant remains constant. What is the total value of r going on increasing? You observe. So that means here, in respective cases, whichever the case we are using here, which term is very fastly increasing, the term growth rate is high for x square time term. That is, the highest ordered term is going to be considered as a our notational representation. So x square we considered here. That means here the big O notation is whose simplification. Can we justify it? Yes, we can justify, because it only makes sense for the larger problems, but smaller problems it doesn't make any sense actually. That is for sufficiently large problem sizes only, the highest order terms are going to be swamps of all the tests. You take smaller values for x is equal to 10, not much difference. X is equal to 100, okay, a little bit. But you observe for x is equal to, you are going to have 10 lakh, 1 lakh, then how the term is going on increasing. X square itself is increasing 10 power 10. So that's why the remaining terms are going to be very, very negligible to other terms. For higher values only, it holds good actually. So I have drawn here and for each term here. This is the entire expression we represented, how the expression is increasing as x is increasing the values. And this is x square time, this is 3x term, this is 5. You please observe the graph. 5 constant. 3x a little bit increases there. But as n increasing, it is increasing, x square time is term is increasing very, very fastly. So fast growth is there in x square term. So that way highest term is considered. Comparing the growth of this x square, these two terms are negligible. That's why we will represent always our asymptotic notation of any expression in terms of the highest order term only. Hope you understand by this time why we considered in the previous examples the second and third terms. For example, in this example, we didn't consider n cube is there, n term and fifth term not considerable by us. But mathematically it's okay. But even because the growth rate or growth function of the lower order terms are very, very slow comparing with the higher order term. So that's why we will consider only the higher order term. The growth rate is represented in terms of the higher order terms only by ignoring the lower order terms. That means, for example, x is equal to 1 to 10, this is happening. If x is equal to 20, you observe how steepness is there. Almost our entire expression value is almost, the growth rate is almost on line with our x square only. These two terms are very, very negligible. That means if x is going on increasing, what happens to us? The higher term plays a vital role in expression value growth also, comparing with the lower order terms. So that's why this asymptotic analysis, when we are using this asymptotic analysis, we will eliminate the lower order terms. Just now as I explained you, 5 and 5 means I will consider only the 4n only. 4n plus 5 means we will consider 4n only. Okay, 0.05 n log n, 2n is also there. But n log n is the more growth related function. So that's why we will consider as a 0.5 n log n term only. 2n, 2 power n, n cube plus 3n, third equation. What is the highest growth rate? Rate of growth is going to be highest in which term? 2 power n. So that's why the highest growth or rate of growth is available. That term is going to be considered in this example. 2 power n is. That means the elimination of. You can use our previously we used to solve can be solved, equations can be solved, or we will eliminate all lower order terms. That is the terms which are having the less growth rate comparing with the highest growth rate term, and eliminate the lower order terms, and also eliminate the coefficient of the higher order term. Then the respective value is considered as our asymptotic notation. So here for order of big O of n or any other notation can be considered. Big O of n log n, coefficient is ignored. And here coefficient is ignored, so big O of n log n actually. So we are going to use like this directly, you can easily identify the analysis can be represented. Generally this big O are going to be used and we will use the common names as big O of n means constant time complexity we will call. Logarithm log n means generally it will be to the base 2. It can be to the base 10 etc. also can be considered. Logarithmic we will call. Order of n will be considered as a linear time. N log n is log linear. And n power 1 plus c, some constant c is there, that is the n power. N square means quadratic, n cube means cubic, etc. N power 1 plus some constant is superlinear, we will call it as. And n power k is some polynomial, kth constant. And some constant power k is there, exponential, we will call it as. So you observe here the common time complexities are going on. Better cases are going to be towards the constant time. Worst case is towards exponential time. So as far as possible, when we are comparing, if you are able to represent the time complexity or space complexity of your algorithm, any of these notations, so that what happens, the comparison can be done by us very easily. Because of this, rate of growth is going to be very fast or high change is there. Those are worst cases, and the change is very, very slow, as well as the low changes are there. Those respective complexities are very effective things actually. In addition to this, big O notation, omega notation can also be used, as well as theta notation is also used. Omega notation is known as asymptotic lower bounds notation. As big O notation is asymptotic upper bound notation, and omega notation is asymptotic lower bound notation. So this function f of n is going to be represented omega of g of n, and which satisfies the condition f of n is greater than or equal to here. Because here lower bound no, so we need to find out the g of n value as a lower bound value, such that above that all are going to be possible complexities. So you observe here, this is our function f of n, and constant times g of n is moving like this. At one position is equal. Below that there is no any such type. Now above that you observe, as f of n is increasing, our g of n is also going on increasing. At a particular position both are going to be equal. Omega can also be used to denote all lower bounds. Like big O is all upper bounds, no? Similarly, all lower bounds are also possible. So, one of them is going to be least, we will call it as a greatest lower bound, or theta lower bound will be there. All other things are, all other lower bounds are considered as a, and lower than that, lower is not possible, no? So, some higher values will be there. Same you are going to consider, but instead of equality is going to be changed, greater than or equal to we have to consider. So the order is going to be same, but the bounds are going to be different here. Previously it is upper bound, currently it is going to be lower bound. That means we have to choose C such that for which value of C our f of n is equal to g of n. Till then it is greater than, if our f of n is greater than g of n, there we are going to, there onwards it is going to be equal actually. By using big omega notation, we can represent the time complexities same as the way which we represent big O only. But the difference is there big considered as a upper bounds, here we are considering it as a lower bounds actually. So various examples are there, 3n plus 2, and we will be omega of n, 10n square, omega n square, n cube plus n plus 5, omega n cube. Please observe in all these cases, whatever the justification we consider in big O notation, the higher order term is considered and lower order terms are going to be ignored. But the higher order term coefficient is going to be ignored and it will be represented actually. So that's why by using our omega notation, but lower bound concept is considered actually. One of them is upper bound, one of them is lower. But we want exactly. That means our time complexity must be in between this lower bound and upper bound. Exactness will be there. To represent that, we will use theta notation, that is asymptotic tight bound we will call it as. It's not lower or it's not upper. So there are two constant values will be there. So our f of n is going to be between c1 of g of n and c2 of g of n. It is equal to g of n for some values of c1 and c2 actually. That means this lies between upper bound area and lower bound area can be considered. Common area between these two cases actually. So f of n is equal to omega of g of n and f of n is equal to big O of g of n. If both are equal, then we will represent them as a theta of g of n. That is, our upper bound value and lower bound value are equal, then we will call it as a tight bound. Then in such cases, we can represent it by using a theta notation. So, we are going to represent if both upper bound and lower bounds are equal, then we can start representing. You observe here, according to the expression, at some point, all of them may be equal. Above that, all as f of n is going, your C2 of g of n is going also, C1 g of n is going also. But upper bound and lower bound gap. In between, this area will be considered as our tight bounds actually. So, these three are various notations we are going to use to represent our algorithms actually. Algorithms, time complexities. Same way we can use here. So, we need to find out C1, C0 and C1 such that our f of n is equal to g of n, and in other words, we can say by using big theta notation, we can represent the time complexities by selecting the proper C1 and C2 values actually. So if you are going to consider here, on some more example, all items twice we are using. So even though twice we are using, there is no much difference. Individual for loops we are using, 2 times we are using big O of 2n, which is almost the same as big O of n only. And also pairs of numbers also, big O of n and n square is there. You observe here, when tabular column is there, this is executed n times and this is executed n square times. So total time number of instructions, that is executable instructions are going to be n plus n square, and the highest term is n square. So we will represent it by using the coefficient of the highest term. So by using all these three notations, we can represent our algorithm time complexity. Of course, depending upon the either upper bound consideration or lower bound consideration or tight bound consideration. Another example is the small o notation. The asymptotic upper bound provided by big O notation may or may not be asymptotically tight. As I told you, order of n is there. So if order of n is there, order of n square is also there, n cube is also there. That is next all higher levels are possible. But it is not tight, no? So that's why we will use this small o notation or little o notation we will call to denote the upper bound that is not asymptotically tight. That means we generally represent these f of n is equal to small o of g of n. If for any positive integer c greater than 0, there exists a positive constant n greater than 0 such that our 0 less than or equal to f of n less than cg of n actually. So this is going to be represented as limit tends to infinity, our f of n and g of n slash g of n is going to be 0. Then we can consider tight upper bound is going to g of n is an upper bound of f of n that is not asymptotically tight. So that's why the difference in this definition is here comparing with our previous case is specified as here we are moving that upper bound g of n is an upper bound of f of n, but it is not asymptotically tight. Similarly, small omega notation can also be considered. For a given g of n, little omega can be considered. So in case of little omega function, there exists an n naught greater than 0 such that for all n less than or greater than or equal to n naught, 0 less than or equal to cg of n less than f of n. That is, tight lower bound is going to be not possible in case of our normal omega notation. There we can use this small omega notation. So the order of notations big O, omega, theta are going to be little o are there. So in summary, these are all definitions. Big O is upper bound, omega, big omega is lower bound, and big theta is tight bound. Little omega is strict upper bound, and similarly little o is strict upper bound. Little omega is considered as a strict lower bound. So one more thing we can add, little omega is considered as a strict lower bound. So depending upon the bounding values we are considering, we will represent the respective algorithm by using any of the notations. So, just we comparing relations here, you observe yellow color is going to be considered, colored will be considered as the respective notation. So, if your time complexity is time, that is theta, it is between lower bounds and upper bounds, this area, it will fall strictly within that, you can represent them. And this is represented omega, big O. Big O means this is our CGN. This is the upper bound notation, no? So that's why below that all are possible. And in case of this is lower bound notation. So above that all are possible actually. That means all possible cases are going to be identified so that if the respective thing we are representing is upper bound, lower bound or a strict bound, tight bound, based upon that we will use the respective notation actually. There is a small relationship between among these theta, big omega and big O. For any two functions, f of n and g of n. F of n is theta of g of n if and only if f of n is equal to big O of g of n and f of n is equal to big omega of g of n. Already we discussed, if our function is both having the upper bound as well as the lower bound, then we can represent with our time bound. That is our theta notation. Theta of g of n is big O of g of n intersection omega of g of n. You observe here, this is our big O, this is our big omega. Intersection of these two means it falls like this. That is the relationship between our theta, omega and big O notations. Now you observe graphically, this is an yellow part in big O. This is our constituent base. You observe here, this is CGN and this is going to be CG. Fn includes in both cases. Right? So this is your C2 CGN, C1 CGN. And in between we have that is represented by omega actually. So the running time of f of n is worst case big O of f of n. If big O of f of n bound on worst case running time implies that big O of f of n bound on the running time of every input actually. That is worst case. Theta of f of n bound is on worst case running time does not imply that theta of f of n is bounding the running time of the every input actually. Big O notation is based for every input it satisfies. Theta notation, it need not satisfy for every input actually. In case of omega, best case only. So running time of omega of f of n is implies means best case is the omega of f of n is can still say worst case running time of the omega. That means worst case running time is given by some unspecified function g of n belongs to our omega of function n actually. So to summarize, these are the various three notations we will use in general, and to represent our theta notation, set of all functions that have the same rate of growth as our g of n, and big O notation means set of all functions that whose rate growth is same as the or lower than that of the g of n, and big omega notation is set of all functions whose rate growth is the same or higher than that of the g of n. So that means your theta notation is asymptotically tight bound, big O notation is asymptotically upper bound, and big omega notation is asymptotically lower bound actually. By using these notations, we can represent our time complexity or space complexity or any other parameter can be represented, which is based on our growth rate of the function actually. Thank you one and all for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.